Okay, we're good to go? Okay, so I've been asked to give some kind of introduction to containers with the hope that we'll see some connections to lenses, right? And I thought about this, and I think I'm just going to present this from the perspective of containers, and then we can find the connections later. I think it would do containers a disservice to see it just through the lens of lenses. So I'm going to focus. This might actually be distracting, but I'm going to focus on this as a theory of data types, and then we'll see that there are connections. So some names that if you want to Google for references, then names to put into Google would be, good names would be Abbott, Altenkirch, Ghani, Gambino, Highland, Joachim Koch, and many others. I'm sure this will appear on the wiki eventually. Right, so the idea is to have some kind of theory of data types where we want to talk about all data types, and we want to be categorical. So we're usually thinking of initial algebra semantics for data types, which means that we are modeling data types as initial or terminal algebras of a functor. So this is very nice. It neatly packages up exactly what we need when we deal with data types. It gives us formation rules, introduction rules, elimination rules. But unfortunately, not every functor has an initial algebra, for example, right? So the typical example is the functor f of x equals x arrow 2, arrow 2, right? Where 2 is the two-element set, for example. So I have to do a double arrow 2 because otherwise it's not even a functor. But this way it goes from contravariant to covariant again, right? So this, for example, goes from set to set. But if this had an initial algebra, then in particular, this initial algebra, which I could call mu f, would satisfy that mu f is isomorphic to f of mu f. Right? That's one of the properties of initial algebras.
So it's like equivalent to the continuum hypothesis?
No, even worse, right? I mean, in classical logic, this is the power set.
Yeah.
So this would say that there is a set such that it's isomorphic to the power set of a power set of itself, right? But the cardinality on this side is, well, let me write this down here. The cardinality on this side would then be equal to 2 to the power of 2 to the cardinality of the same thing on this side, right?
Yeah, what I'm saying is that if the cardinality is F0, you accept the continuum hypothesis as false, then this is not a problem.
No, because this is Cantor's theorem that there is no set such that its cardinality is equal to the cardinality with power set, right?
Yeah, no, it will still be.
This is Cantor's paradox. This is just plain false.
Take a single power set, no?
Yeah. So in some sense, it's even worse, right? Just one of these arrow 2 would be enough to get into trouble, but now I make it even larger, right? So this functor cannot have an initial algebra or a terminal coalgebra because we have the same property, right? So what does this mean? It means that we can't just say data types are given by functors and we take their initial algebras. We have to restrict to a nice class of functors that actually have initial algebras, right? Okay, but then this is a bit problematic because now we have to figure out what a nice class is, right? It would have been much easier if you could just say all functors are nice, and then we're done. So what do we want to capture? So we want to, in some sense, capture all the things that data types are, right? So what can you do with data types? Well, we can put things in them, right? And we can manipulate them. So what are some examples? Well, for example, a tuple should be some kind of data type, right? I put two things in, and I can take them out, and I can combine them. Or a list of things could be a data type. Or a tree of things. Maybe I store things at the leaves, or I store things at the nodes. Or any kind of things like this, right? So what do these things have in common? Well, let's see. So I'm going to show you a particular way to see these things, and then we can abstract from this to see if we can get something from it. So tuples, first of all. One way to see a tuple is that a tuple of x's, right, is that it's a fixed thing, and then I have two places where I can map into my set x or my type x or whatever, right? So to give a tuple, I have to give two things in x, right? Or to give a list, well, I can give the empty list, or I can give the one-element list, or I can give the two-element list, or I can give the three-element list. And for each one of these, I have to map certain things into x in order to give the elements of the list, right? So here I have to give one thing in x, here I have to give two things in x, here I have to give three things in x, etc., right? So I'm just trying to make this look a little bit like the tuple, where I had to give things in x in order to fill up my data structure, right? Or if I have a tree, then first I really have to decide the shape of my tree. Should I go always to the left? Or should I maybe branch like this? And then in each case, I have to fill in. OK, so maybe I have data everywhere, right? At the end, I have to fill in the positions where I expect to find data in my tree. And this is a map into x. Right. And it could be that two of these map to the same data, right? I'm allowed to have the same thing in different positions in my data structure. So what I'm saying is that each one of these data structures is conceptually given by, first, there is some kind of choice of a shape, which here there's only one shape. Here I have to choose how long my list should be. Here I have to choose the shape of the tree, literally, right? And then afterwards, I had some positions in my data structure to fill with payload, with data, right? So this is given by, all these situations are described by a set S of shapes. And for each S in S, so for each shape, a set P of S of positions where data goes. So that means that in order to describe any one of these, I have to choose S, which is a set. And for every S, I have to choose a set of positions. Right? Alternatively, I could package up this data as from a set P prime into S, which just tells me every position which shape it was a position for, right? So if I start with this data, then I take P prime to be a choice of S in S, P of S, and then this is just a projection. Or if I have one of these, I can take this one to be the inverse image of the function, right? So I can go between these 2 points of view. Here I have a family of positions up front. Here I have an internal family, just a morphism in the category, right? Let's see where I want to go with this. OK, so this is the data that determines a container.
So for lists, S is the
Are you going to go over the list?
Yeah, I'm going to go over them. Yeah. So we usually write, for some reason, when we want to say that this family is signifying a container, then I write S, and then a left triangle and P for the container. So it's just notation.
Do you know the latex symbol for that?
Left triangle, I believe. Yeah. Okay, so what I should have said before is that the goal of all this, is this falling now? So what we are on the lookout for is a category cont C of containers together with a functor from this category into the functor category on C, end of functors on C, right? And what I've described here is just the case when C equals set. So this comes back to the original motivation, right? We want to find a nice class of functors. So we're going to find another category which we can deal with, and a way to interpret these functors, this data as actual functors, and these are our nice functors, right? And it will turn out that this thing is actually full and faithful. So we really have a good representation of these things, right? We can reason about the actual things, well, on either side, just by going back and forth along this functor, right? Right, so for this talk, I'm going to take C to be a set, but in general, this works for any locally Cartesian closed category with extensive coproducts. So basically what this means is that locally Cartesian closed famously means the internal language is dependent type theory, right? And extensive coproducts means that the coproducts in this type theory play nicely. So what this means is that everything I'm doing now, you can just do in the internal language of the category, and it boils down to the same thing, right? But I think it's clearer to just work in set for intuition, and then you can translate it. Okay, so what we're doing is we're trying to find this category cont set in this case, right? And I've told you what the objects of this category should be. It should be an S and a P like this, right? A shape and a position. Right, so let's see if we can actually get these as in this format, right? So what should be the shapes and positions for a tuple? Well, there's only one possible shape, right? There's always exactly two things in a tuple. So this should be given by the one element set as the shapes. And then I always have to give two things in X, right? So my positions should be the two element set, regardless of this thing from the unit set, right? Okay, let's do lists. This is a little bit more interesting, right? Okay, what does it mean to choose a shape of a list? Well, it just means that I choose how many elements I want in my list, right? It's either the empty list, or it's a one-element list, or a two-element list, etc., etc. So the shapes are given by a natural number n. And what are the positions for a given natural number? Well, that's actually, I need that many elements from X, right? So if I choose this to be the finite set, then to give a container of this shape means that I have to give the length of the list and then that many elements of X, right? That's exactly what the list is. And finally, for trees to cheat and say that the shapes of a tree is just a tree with dummy data in it, right? Such a thing, if you think about it, is exactly the paths through this tree. You have to navigate down the tree to each position in the tree. So it's a bit, so it's enough to specify the simpler case and then what it means to be a path in this, and that gives you the general case of actual data in it. But okay, so that's the intuition behind this category, or the objects of it. Is it clear so far? Maybe. So let's see if we can start working on this functor. So we haven't defined the morphisms here yet. Yeah.
Technically, like, so the second should be like a function, no, like a,
Yeah.
a function from.
For every s, you should give a set.
So it's just a function, right?
Yeah, it's just a I mean, if you want, if you don't like this notation, you can upgrade this to a discrete category, and then it's a functor, right? If that makes you happier.
I understand that
Exactly, but then for lists 1 to n, is it what? How do I get? What is it?
So this n is the one I choose here, right? So this thing here, or if, well, let me write it the other way around actually.
It means that for every n, take the set from 1 to n.
If you give me an n, I'm going to give you back the set which contains 1, 2, 3 up to n. Right?
Okay.
It's the finite set with n elements.
I understand that a triangle represents the container, but I don't understand the notation. Like,
It's a dependent sum thing. I think dependent sum
Yeah,
is
yeah.
easier for me to read.
Yeah, so it's a choice. I mean, it's all, this is all it is, right? I mean, just to notify that I'm treating it as a container, I'm writing a triangle, but it doesn't really mean anything.
yeah, so like when you say 1 triangle 2, that basically just means 2 things.
Yeah, it means that the set of shapes is 1.
Okay, so the one on the left is the index of the dependent sum, and the one on the right is the thing you're summing?
No, the one on the left is a set,
Yeah.
the one element set, and the 2 on the right is the
Well, it's the constant, right?
constant 2, right?
So on the left, he binds the name as well that he's using on the right. So it's like in a dependent sigma. Yeah, it's a sigma fashion.
Yeah.
Yeah, that was what I was asking. I said,
Yes.
is this the index of dependent sum on the left and the thing you're...
No, so the index here is implicit, right? For every,
Yeah, so the one on the left is the indexing set.
it's the indexing set, yes. It's not the index, yeah.
Yeah, okay.
Is it worth saying tree again or not really?
Please say tree again.
Is it worth saying what?
Explain the tree.
Ah.
Anyone?
So I'm saying that the shapes of a tree are just kind of boring shapes with no data in it. So that's a particular choice of a shape, right? Or where I don't have any data, I'm just storing the branching structure of the tree.
Yeah. I guess you'll probably tell us more precisely what it is later anyway. Right?
Maybe not, so maybe we should do this now. So here's one possible shape of a tree, right? Here's another possible shape of a tree. And I'm saying these are the shapes. So first you have to choose kind of the scaffolding of the tree, right? And then you have to say for what are the positions in the tree? Well, I want to describe all these little dots, right? And this exactly corresponds to the paths in the tree. So one path is just stay where you are, right? Does that make sense? No?
I mean, once you told me the shape of the tree, it seems like you've already told me what points in the tree. But
So the shape is the whole tree, right? So
data labels on the node of the tree.
so this is one shape, it says, well, I have a branch, and then here I finish, and here I have just one child, right? And the positions of this one is a 4-element set. It's the node, the root, it's this thing, right? I'm running out of space.
So by path, do you mean path starting at the root and not backtracking?
Yeah,
Yes.
path starting at the root, going down, and stopping wherever you want, right?
So a tree is a collection of paths.
Yeah. Well, and then you have a function from the paths into X, right, where you store the data.
How is that different from the set of nodes of the tree? Exactly, which you've already told me. Nodes. It's exactly, it's just a set.
I think it's easier to distinguish between the paths if you have the full data instead of just taking the.
Well, how do you,
I mean, it's
how do
like
you get
lists.
a set of nodes?
Yeah.
Because
A list is a tree.
then you have to tell where
Yeah.
the nodes are. That's
Yeah.
the problem.
But what does it mean to R?
So the nodes are somewhere in the tree, right?
I think it, yeah.
Yeah.
We should just go on.
Yeah.
Maybe we should actually just do it as a using cache or something. As
Yeah.
a greater thing.
Also, maybe there's a big confusion how you build a tree like as a functional data structure.
But then he'll tell us when he tells us how to build polynomials, right?
Yeah.
Yeah, okay, so the tree, right. So I guess the confusion is that this theory really insists on this shapes first, positions later, right? Whereas for trees, this is not a very natural distinction. You would just like to give the whole tree in one go.
Yeah.
Okay, so let's see if we can define this functor on objects, because this is how we should really think about these things, right? They're not worth much on their own. They get their value from the fact that we can actually represent functors with them, right? So if
Container morphisms are just bundle morphisms.
we'll get to container morphisms later,
Okay.
but I mean it doesn't, right? Because I want to think of this as representation of this. It doesn't make much sense to think about the morphisms before I know what they represent, right?
Okay.
So if I have a container SP, then I would like to define a functor from set to set, which should capture this intuition that we maybe hopefully have, right? So what should we do? Well, given an X, what does it mean to be data in this container? Well, what I've been saying so far is that you should choose a shape, and then you should fill the positions with data, right? So choosing a shape means that we take a disjoint union over all the shapes. So I choose one of the particular shapes, and then I give a function from the positions of this shape into X, right? So now we can also start to see why these are called polynomial functors, because this is a categorification of a polynomial function, right? Where it's a sum of exponentials. And you can say, what is there a question? Yeah?
So I want all shapes, so maybe it's the product, no, instead of sum. It's more natural to me. Like you are able to choose whatever shape you want, and then you can choose whatever position you want. So to me, it sounds like the product, not sum.
Right, so it's the choice of perspective, right? So product means that to give a value of this type, you have to be able to deal with every shape, right? Sum means that you get to choose which shape you want. So for example, to give something in a list, you choose how long the list is, and then you fill the list, right? You don't have to give a list for every length.
Okay.
So that's why sum should be the right choice. Right. Okay. Is that clear? And we can see that this is functorial, right? Because if we are given a function from x to y, and we're given something in this thing at x, so that consists of a s, and then some function h from ps to x, right? And now we have to do the same thing. Oh, this is now falling down.
Oh, that's
Maybe it's fine. So now we have to give a new shape, and we have to give a function into y instead of into x. So what can we possibly do? Well, we have a shape, so we can reuse the same shape. And now we have to give a function from p of s into y. But we already have a function from p of s into x, and we have a function from x into y. Right? So we can just compose these. First we do h, then we do f. So this gives an action on morphisms.
I don't understand, like, the definition of a functor, how do you define the functor from ps to x?
So this is just a function, right? P of s is a set, x is a set.
Yes.
So I'm forming the function space.
Oh, so you mean, okay, so that is the function space.
Yeah.
Okay. I thought it was a type of a precise function. So no, okay, that
No,
is
yeah. So this is why you need to be locally Cartesian closed, right?
Yeah.
So that you can form function spaces. Okay. So, and this is obviously associative and has a unit, right? Because it's morally just function composition. So that's fine. Okay, so what about morphisms? So we want morphisms here to represent natural transformations here, right? So let's look at some examples. So what are natural transformations? These are intuitively things that doesn't really look at the x, right? So I should be able to either use the functorial action on x before or after I transform, right? So
sorry, are you doing homomorphisms for what? For double bracket?
No, so I'm going to do morphisms for things here and see what that requires me to do here, right?
Because it's full of faithful, so you know the morphisms. I would have been Cortez we know well.
Okay, yeah, so right. So you could define the morphisms here to be things in morphisms of the image, yeah, but that would be cheating, right?
So you're doing like morphisms in CR?
Yeah, that's what we're going to find out now. Yeah. So I could do that. That would, first of all, be cheating, and more seriously, it would mean that I would have a large representation of morphisms. So,
sorry, so these are the objects.
These are the objects, yeah.
Okay.
And we don't yet know what the morphisms are, right?
Could you repeat what the question was, because I couldn't hear the question. So I'm trying to infer the question from the
Right.
My question?
The question that Brad just to the discussion.
So Brendan said, since you want this to be full and faithful, why don't you just define the morphisms here to be the morphisms in the image here, right?
Okay.
And then it will be full and faithful by definition, right? And then the main reason not to do this is that you want a small representation of morphisms and not a large one, right? Just like this is a kind of small representation of this large functor space, right? Okay, so let's look at one particular thing which I would like to be able to represent, which is the flatten natural transformation. So this takes a tree full of x's and gives me a list of x's where I've actually flattened out the tree, right? So you can check that this is natural over here, right? So what does it do? If I have a tree, something like this, so now I guess my trees, this is tree prime, where I only store data at the nodes, at the leaves, not at the. So it takes a tree and it just flattens it out to a list, right? So this thing gets sent to here, this thing gets sent to here, and this thing gets sent to here, right? Is it clear what this function is doing? So this is something I would like to represent. So what are we doing? Well, it looks like we're mapping each shape over here to a shape here, right? And then you might think that we're mapping each position here to a position here, right? And saying this one goes here, this one goes here, this one goes here, right? Okay, so that's one candidate. We're saying a map on shapes and a map on positions. That seems very natural, right? But let's look at another one, which I'm calling double, which this time goes from list of x to list of x. And if I have a list A, B, then I want to send this to A, B, B, right? So I'm just doubling every element in my list. And this is also natural because I'm not really looking at the elements, right? It doesn't matter if I map them across before or after I do this. So again, I'm sending each particular shape here to a shape here, right? I'm just saying I want twice as many elements in my new list. But I'm not sending each position here to a particular position over here anymore, right? Because this A is going into two positions. So this shows that it's not right to just have a forward map on positions. What I can say is I can say for every element here where it came from, right? So what I'm actually doing is I'm mapping this A back to this one, and this A back to this one, and this B back to that one. Right. So we were tricked in this example because they happen to be in one-to-one correspondence, right? But really, these things should go backwards, not forwards. Right. So with this motivation in mind, we can define a morphism from SP to S prime P prime. You can say that this is given by first a map on shapes from S to S prime, and then for all S in S, I want a backwards map on position. So this should go from P prime of F of S to P of S. So I have to use the F to kind of fix up the types, right? So let's go from P prime of the thing I mapped the shape over to, and then I go back.
These are the morphisms, so which category?
So these are the morphisms in cont set from container. Right. Sorry. Some.
But didn't we already define out the square bracket functor acted on morphisms in cont C?
No, it acted on objects, and for every object, that is for every container, it gave us a functor.
Oh, so we were
So the functor has an action on morphisms.
Yeah,
right?
okay.
So
the idea is that after you build this functor, the end of functors on the image of this will give you the good end of functors for which initial algebra exists?
exactly, yeah. Okay. So a forward action on shapes and a backward actions on objects, on positions. And then, so this was the thing that Jules was alluding to the other day, right? So now, to give one of these for every s, this, if you want, is the same as giving something out of the disjoint union, right? And if it happens that this thing does not actually depend on this, then this just becomes a product, which makes this look exactly like a lens morphism, right, or a lens, because we have something from S times P prime to P. So this is the update of a lens, right? But maybe we can get back to this later. Okay, so we have now the morphisms over here. Let's make sure that we can map them over the functor category.
Sorry, can you explain again how the sum appears?
Right, so it's just saying that to give a function for every s is the same thing as to give a function out of the coproduct. Right? It's the universal property of the coproduct.
The first one, there's a parenthesis around the...
Yes, I should.
We just pull the limit out of the...
Oh, so the parenthesis changed.
Yeah, sorry, I should have been clearer. Yeah.
Sorry, I thought it was the same thing twice, but with a sum.
No. So for the functional programmers in the audience, this is just carry on carry, right, to go between these two. Okay, so if we have morphism, how do we map it over to a natural transformation over here? Right. So I have to write this with a little triangle as well. So this should be a natural transformation between the two functors. So at component x, we have to give a function from sigma s in s p of s arrow x to sigma s prime in s prime p prime of s prime arrow x component at x. So how do we do this? Well, given a choice of a shape, S, and some function h of this type, we have to give a shape in the new container, but we have a function f which turns old shapes into new shapes, right? So I can give f of s as my shape, and now I need to give a function from p prime of this shape into x, but I have exactly the g that turns p prime of new shapes into old shapes, if I start with that, g of s, and my h, which takes me into x. So I've given myself exactly the data I need in order to define a natural transformation. Right? Okay, so of course you have to prove that this is natural, etc. But again, this just comes down to the fact that this is using composition, which is very nice, right, and very natural. So this shows that this actually is a category, and that this actually is a functor, right? So let's see if we can prove that this is full and faithful. Right, and one nice thing is that here I have a very small representation of something very large, right? The natural transformations quantify over sets. So that's something very large, whereas here I just have two functions that quantify over a particular set. Okay, so there's quite a huge proof that this is full and faithful, so I think it's worth doing this. So full and faithful means that the morphisms in the image are in bijective correspondence with the morphisms in the target of this functor, right? And the morphisms in the image are natural transformations. So I want that the natural transformations between interpretation SP and interpretation S prime P prime, that this should be the same thing as container morphisms from here to here, right? And Junera is going to be the thing that gets us there, right? Okay, so let's expand what this means. This is a natural transformation from sigma S in S, P of S arrow blank into this other thing. Okay, and now we're going to use the same trick again, right? Which says that a function out of a coproduct is just a product of functions. So this says for every S in S, I have to give a natural transformation from P of S arrow blank into this other thing. Okay, but now, as Fab pointed out, this is exactly Yoneda, right? Natural transformations out of a home set is the same thing as just this other functor applied to the codomain of the home set. The domain, sorry. So this is for all S in S, we have something in S prime, P prime applied to P of S, right? This is the only bit where we actually have to be clever. Okay, so now we can expand this out. So for all S in S, we get a choice of an S prime in S prime, and then a function from P prime of S prime into P of S. That's my argument. And now, one final bit of general juggling. To have a product of coproducts is the same thing that for every S, you choose which summand you want to be in, and then for every S, you also choose something in that summand, right? So this is the same thing as a choice of a function which for every S tells me which S prime I want, and then I have to give something in that summand. That's P prime of F of S arrow P of S. Right. It's just distributing a product over a coproduct in the category of sets. So this is why you need a little bit more extra structure on C in general in order to make sense of this. Right. And now we see that we've ended up in, sorry, and then for every S here. Now we've ended up with exactly this definition, right? And of course, if you want to do this properly, you have to go back and check that all these isomorphisms are natural, right? But of course they are. Okay, so one particularly nice thing about this theorem is that we can now verify things about the category of containers by working in the functor category, right? So, for example, to show that this category of containers is complete and co-complete, it's enough to just verify this by going over into the functor category and working there. And then, so let's do that. This is the last heading of everything, closure under everything. So let's say that this implies that cont C in general is closed under everything you can think of, right? So products, co-products, composition, if you think of it as functors, right? If I have two functors that are containers, then their composition is also a container. The identity functor is a container. In general, limits and co-limits, but also initial algebras, final co-algebras, constant functors, basically anything you can think of, right? So let's go through a few of these, maybe. Let's start easy with, let's say, the identity functor. So I want to represent the functor which sends x to x, right? So what does this mean? It means that I have to write this in the form of a container functor, right? Okay, but I can do this by saying that x is the same as 1 times 1 arrow x, right? Which in turn is the same as sigma something in 1 arrow x, which is the interpretation of the container with one shape and one position applied to x, right?
What was v and k in the list above?
So this is a new, so the final coalgebra, and k for constant functors. Okay, so let's do the constant functor for fun. So the functor which sends x to some fixed set a, then I could always write a as a times 0 arrow x, right? So this shows that the constant functor is given by the container which has a shapes and 0 positions, right? Does this make sense? Okay, let's maybe do products. So if I have two containers and I want to show that their product is a container, so first of all, products in the functor category are pointwise, right? So what I want is I want that if I have one container, S in S, P of S, arrow X, times another one, so S prime in S prime, P prime of S prime, arrow X. Then massage this until it looks like a container again, right? So first of all, in order to give something in this product, I have to give something in the first factor and then something in the second factor. In the first factor, I have to choose an S. In the second one, I have to choose an S prime. So I could rearrange this and say that this is the same as choosing an S and an S prime in the product of S and S prime. And then I have to give a function from P of S into X, and I have to give a function from P prime of S prime into X, right? We just pulled out this S and put them together. But now here I have two functions into X, and I know that to give two functions into X is the same thing as giving one function from the coproduct into X, right? This is the same as giving a function from P of S plus P prime S prime into X. And now I got it in the form of a container functor again, right? So this is, by definition, the interpretation of the shapes S prime and position blank plus. So one thing to note with this example is that in order to get products in cont C, I had to use products and co-products in C, right? So this is a general fact that you don't get that cont preserves limits on their own. You need both limits and co-limits in order to get limits in the container category.
I think this arrays works for any extensive locally Cartesian closed category.
Yeah.
The extensiveness comes when you switch the product and the co-product.
Yes. Yeah.
And you don't need something special about one, like everything's a co-product of ones, or that one's a generator.
No, I don't think so. No. Okay, so the trick is you work in the internal language, right? And then you do the same proofs, basically. So
Is it possible to quickly re-go through the proof? Because I don't understand some of the passages.
this proof,
Yes.
full and faithfulness.
Yeah.
Okay. Okay,
So
so
you start, the first equal is by definition, you're just saying that's an homomorphism of functors, so you have a natural transformation.
Yeah.
In the second one, you're unpacking what
yeah,
SP means, and then what happens?
and then so Juneda is the next line, right?
Okay. Cool.
So this line is the universal property of coproduct, right?
Okay.
So this is, I mean, plus a little bit of natural transformation juggling, right? So it's at each component, this is a function out of a coproduct, right? Which is the same as giving a function for every summand of the coproduct.
Component, that's a function out of the component. Okay.
It's just commuting a sigma and a hom, right?
Now, why you can apply Yoneda in?
And now inside here, I have a natural transformation from a hom into another functor.
Why is the first a hom?
Because it's a function space in set, right?
What do we mean by underscore there?
Underscore means this is where you put the argument, right? It's
I really hate these arrow notations. Okay, now I'm understanding this.
Yeah.
Great, cool.
so then then Juneda applies.
Yes,
right?
then Yoneda applies, I do agree. Okay, now then the rest is clear. Yes.
Right, but this pi should be a sigma, right? That's important.
The second pi is a sigma. Right.
So we're just unpacking this definition.
No problem. Here is your sigma.
And then finally, we use the fact that in order to give something into a sigma in set, it's the same as to give a function on the indices plus a function on the summands. Right?
Is there a concise way to say this?
So it's, if you read this as for all and this as exists, then it's the axiom of choice, right? Except that it's the constructive axiom of choice, so it's provable.
Okay, cool. Thanks.
May I interrupt for a second? Just gonna go to the city, or we, I mean, Emmy, and get some things like food, toilet paper. So if there's anything that you want in particular, that was a good moment to say that.
People like the chocolate, myself included.
I don't have.
Order.
Right. I don't have that much more I wanted to say anyway. So, so there's one more closure under. So one more closure under a constructor that I would like to point out. Let's do closure under coproducts. So we play the same game again, right? We take two container functors, take the coproduct and see what we can massage it into. Okay, so what does it mean to choose between these two? Well, no matter which side you choose, you have to choose between giving a shape in S or a shape in S prime, right? So this is the same as a choice of an X in S plus S prime. And then, depending on which choice you made, you either have to give a function like this or a function like this, right? So if X is in left of S, then now you have to give a function from P of S to X. And if X is in right of S prime, then you have to give a function from P prime S prime into X, right? Okay, and then, so we see that this is the same thing as the container, where the shapes are S plus S prime, and the positions are given by this function, right? Applied to X. So the reason I want to draw attention to closure on the coproduct is that even if P and P prime are non-dependent, right? They don't care which shape you're in. The resulting coproduct does care which shape you're in, right?
What did you mean that it's closed under initial algebra?
So I'll come to this next. Yeah.
So this explains why the category of lenses doesn't have all coproducts.
Yeah.
In general, a coproduct in lens gives you a container.
So this in some sense is why this category is nicer than the category of lenses, right? Because you need to enlarge your universe a little bit so that you can stay.
Is it just the closure of the category of lens or something?
Good question.
Wow. Oh, under plus.
No, I think it's bigger than that. I mean, that would be a miracle if it is.
At least in set, it's closure
It's,
under his plus.
I don't think it is, but there is a connection. So another way to see so this again only really works for set, but cont set, another way to see it is that this is fam of set op. So it's families of objects in set op. And fam is the set index coproduct completion of this category.
Is the what completion?
Set index coproduct. So, so there is
because set index coproducts
of the underlying category, op. But of course, so lens is not set up, right? So.
No, but I think it still works. I mean, I think.
Yeah, you could do this too. Yeah.
At least it's very similar.
It's similar, yeah.
This would be actually remarkable if this is the closure of lens under coproducts, because this also has tons and tons of properties that lens doesn't have. Like, if you take a pullback in lens, you get one of these as well.
Yeah. But you also have a right adjunct. I mean, yeah.
That would be very nice if that's true. It's possible.
And you can see that, right? In the bundle picture, you see it pretty clearly. Like this coproduct, you just have two bundles and you coproduct them together.
Yeah.
And so you just imagine a lens is like a trivial bundle.
Yeah.
And the sum of, and any bundle is the sum of trivial bundles.
Is that true?
I mean, in set. Any function is this.
Mm.
That tells you that that is geometric.
Okay, so let me explain what I mean by closure under mu and nu as well. So we're not going to do the actual proof of this because there's a little bit more involved, but at the very least I can explain what I mean, right? So let's start with mu. So in order to make sense of this, we need to allow containers of more than one variable, right? So polynomials with more than one variable. So I'm talking about things like a functor from set times set into set, for example, right? And what I mean by this to be a container, well, I mean it's still of the same shape, right? So I have a choice of an S in S, and then I have some positions for X, and I have some positions for Y. And now the claim is that if I now take the initial algebra with respect to Y, so then this is still a container, right? So it's of this form for some S prime and some P prime, right? So you need to generalize to n-ary containers, and then you say that if I have an m plus 1-ary container, then its initial algebra in the last variable is a container, an n-ary container in the remaining variables, right?
How is this relevant to the fact that containers is fully faithful into end of functors? Because you implied there that, okay, you get all products and co-products, but somehow you also get final and initial coalgebras.
Yeah, I'm not sure if it helps in this. Okay. Yeah.
Just to make sure.
Right. So one thing, if you're trying to prove this, so you need to find an S prime and a P prime that makes this work, right? And we can do the easy bit. So one thing that's useful is that whenever you have a container and you want to know its shape, then you can just plug in 1 and see what happens, right? Because so if I have a functor f, which I suspect is a container, if I look at f of 1, if it is a container, then this will be sigma s in s p of s arrow 1, right? So this will just be isomorphic to s because I have a choice of an S in S and then a function into 1, but these are unique, right? So I can immediately get the shape set for any container just by plugging in 1. So if we do this trick here, then we see that S prime, the shapes of this thing, should be this thing if we plug in 1 for X, right? So here's my this thing. So this is mu y, and then 1 for x, so this goes away. And I just have sigma s in s q of s y. So the shapes are exactly the initial algebra of the thing with one less variable, right? So if you now imagine we do this by induction on the number of variables, we've already constructed this initial algebra, right? And or alternatively, this is the base case that we actually have to put in the work and construct, right? And we happen to know that this is something called a W type. So it's a well-founded tree with branching from S and continuations from Q. So I don't expect you to know what this is, but this is one thing you need your category to have, and it's enough to have something like a natural numbers object. And
so this is not true for local Cartesian closed categories that are extensive?
No, you need...
So you have a natural numbers object or something?
Yeah. You need,
can we see that? Like near
So in order to have this, you need a little bit more structure in your category to actually be.
And David's question or remark?
So David's question was, it's not enough to be locally Cartesian close plus extensive. And I said yes. Yeah. You need, I mean, you basically need to have enough regular cardinals so that this becomes continuous. Okay, so you can find the shapes this way, and then you can compute that again, the positions for a given shape is again the paths in this tree. So what this means is that we can define a recursive equation to say that the position for a given tree is either I'm happy at the node, the POS, or I choose a Q in QoS, and then I continue according to my subtrees. So this is a recursive definition, right? So you also have to do some work to justify that this has a solution.
Sorry, I wasn't paying direct kind of attention, but you're saying that in order for this to work, we need to have initial algebras for endofunctors in C, for polynomials in C.
Yeah, for unary containers.
For unary containers in C. Then once we have that in C, then we can form the S prime we need.
Yeah.
And the P prime we need.
Yeah.
Okay. And it says soup?
Right. So this is the tree which has branches. So it's the supremum of all its subtrees. That's why it's soup. But,
subtrees, that's what it stands for?
Yeah, a supremum. So F says for every S in S, I have. Sorry. So David, what I mean is that this thing is inductively defined by this construction. So in order to give a function out of it, I have to say what I do for the constructor. So if you want, it's using the initiality property of this thing in order to define P prime.
Oh, okay.
And this is the equation you have to satisfy. Right. But at a high level, it's again the paths in this tree, right? That gives you the things, and that comes us back to our confusion at the beginning, right? Okay, so let me just mention that this is the simplest possible version of containers, right? Or polynomial functors. We can also upgrade to index containers or dependent polynomial functors. And so the idea is that the containers gives me, let's just stick to set. The containers represent functors from set to set, right? Whereas an index container represents indexed functors for some index sets I and O. I can turn this category into this category, right? So O index set into I index sets, or if you want set slice over O to.
So before O and I were both 1?
Yeah, exactly. Yeah.
But here you already had O as 2.
Yes. But here, O can be an arbitrary, not just a finite set, right? So this only works for finite sets, right?
You're just talking about polynomial functors that have more general.
Yeah.
Okay.
Yeah. So this is indexed containers / dependent. Right. And the idea is that before, the data we gave was just a morphism from P to S, right? Which said for every position, what are the shapes it's indexed by. And in order to make it a dependent polynomial functor or an index container, we also need for every P to say where the output should be. So we have an H like this. And for every shape, we have to say in which input it's valid. Right? So if you take these to be 1, then we always have these maps, and we get the previous case. Right? But this is the general case of an actual index container. And then, in general, the way you turn this into a functor is to use the locally Cartesian closed structure. So this is something like, what do you do? You want a sigma at the end, right? So that's a sigma G. And then you want a product, pi f. And you want to re-index by H star to get the substitution right. But again, you can do this in the internal language, and then I think it's clearer. But I just wanted to mention that sometimes people talk about these kind of containers and just say polynomial functors. And sometimes people call these dependent polynomial functors, but this is the general case. Right? And I don't know what this means in terms of lenses. Right?
Yeah. There's no unpublished note by Martin Hyland, I think, that observes that morphisms of dependent containers are related to dialectica, which is another thing that's basically just lenses.
Yeah. Okay, so I think that's all I wanted to say. We're roughly on time.
I have a question. Do people program with these? Like, are they used for anything outside of theory?
No, like data type generic stuff.
Okay, so they are used in
so
active programming?
Yes and no. So one problem is that some of these, so in particular, this closure means that in theory you could just use containers instead of other data types, right? Because you can just use this, you can just use the closure to get down to one container.
You could build a programming language with just containers and nothing else.
Yeah, but problem is that some, yeah. So the reason type depth is not using containers is things like this. So we use isomorphisms such as this, right? But this is only valid if you have function extensionality. That is, functions are equal if they are pointwise equal. So in ordinary type theory, you can't prove this in Agda. Yeah. So containers are only really well behaved in an extensional type theory, or type theory where you have enough nice things.
I have a probably sidetracked question, but why many type theories underlying programming languages do not assume function extensionality?
Okay, that's not our 5-hour lecture.
No. So the short answer is that if you assume it, I mean, you can assume it, but then now you break your computational properties of your programming language.
So
right?
that's what you do.
Because if you try to evaluate this assumption, then you just get stuck. It doesn't compute, right?
So the thing is, you have these bunch of computation rules that basically all your type theory is based on, and extensionality just doesn't pop out of that. That's just something that you have to put on additionally to get it. And
So
then
it's like giving the type and not the definition.
So there isn't basically a nice extensional type theory which is also computational.
Yeah.
Is cubical type
And
theory supposed to be that?
And nowadays you could use cubical type theory. Yeah.
Sorry?
Nowadays cubical type theory satisfies this particular criterion.
Oh, that's cool.
The downside is you have to learn cubical type theory. Right?
And then you can do this stuff in there.
Yeah.
We'll build our own proof system eventually. Let's first get this thing in production.
So there's an obvious question to us. There's a canonical embedding of the lens category into the containers category, which probably doesn't respect the intuition for both. There's an obvious question that if you turn a lens into a container morphism, that induces a natural transformation between the polynomial and the functors, and I haven't worked out what that is, and it would only take a few minutes.
It's pretty easy.
Yeah.
Is it interesting?
Yeah.
Was it?
I mean, I think I answered your question. Like, how do you see this lens-wise?
Yeah. So you take a lens
Yeah.
that canonically induces a morphism.
Yeah, it's Hom out of one F. Hom out of one blank. You want me to write it?
Yeah. No. Go, okay. I would thought it was something else, so maybe you write it.
No, maybe.
You want me to make it off?
What did you say?
You want me to continue before that?
Yeah, that's where researching that.
I mean, I don't know.
Sure, we can go
I was just saying if you have a map.
I don't know another way to put it. I finished with the presentation.
Yeah. We clapped and everything, right?
clap again.